Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is sp3d3 hybridization, and for this concept I am taking the example of iodine heptaflouride. So our today's example for the sp3d3 hybridization is iodine heptafluoride, that is IF7. So before starting the hybridization, let's make the Lewis structure of IF7. So that's my iodine over here. The first fluorine, second fluorine, third fluorine, fourth fluorine, fifth fluorine, sixth fluorine, and the seventh fluorine. Now let's talk about the iodine first. Iodine. The iodine is the member of group number 17, and that's halogens. And in case of halogens, we all know that halogens have 7 electrons in their valence shell. So that means we have to mark 7 electrons around iodine in the Lewis structure. So that's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's talk about the fluorine. The fluorine has an atomic number of 9, and fluorine is also halogen. So its electronic configuration is 2, 7. That means fluorine is also having 7 electrons in their valence shell. So let's mark 7 electrons around all the fluorine atoms in Lewis structure. So I'm talking about the first fluorine now. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now let's come to the second fluorine. First electron, second, third, fourth, fifth, sixth, seventh. Let's come to the third fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Let's come to the fourth fluorine. The first electron, second, third, fourth, fifth, sixth, and the seventh. Let's come to the fifth fluorine. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Let's come to the sixth fluorine, sorry. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Let's come to the seventh fluorine. That's the first electron, second, third, fourth, fifth, sixth, and the seventh. Now in this structure, what's going to happen? All the fluorine atoms are going to make 1-1 bond with iodine atom. So that's the first bond of first fluorine with iodine. That's the second bond of second fluorine with iodine. That's the third bond of third fluorine with iodine. That's the fourth bond of fourth fluorine with iodine. That's the fifth bond of fifth fluorine with iodine. That's the sixth bond of sixth fluorine with iodine. And that's the seventh bond of seventh fluorine with iodine. Now let's count the number of valence electron of fluorine atom after forming the 1 bond with iodine. So that's the first electron, second, third, fourth, fifth, sixth, seventh, and the eighth. So that means fluorine atom has attained octet, that is 8 electrons, after the formation of 1 bond with iodine. The very similar way, what's going to happen? The second fluorine is also going to attain the octet. The third fluorine is also going to attain the octet. The fourth fluorine is also going to attain the octet after the formation of 1 bond with iodine. The same way, fifth fluorine also going to attain the octet, that is 8 electrons. The sixth fluorine is also going to attain the octet, that is 8 electrons. And the seventh fluorine is also going to attain the octet, that is 8 electrons in its valence shell after the formation of 1 bond with iodine atom. So I'm repeating it again, that all the fluorine atoms will attain 8 electrons, that is octet, after the formation of 1-1 bond with iodine atom. So now let's talk about the iodine now. Now we have to count the number of valence electrons of iodine after the formation of 7 bonds with 7 fluorine atoms. So I'm counting for the iodine now. That's the first electron, second electron, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th and 14th. That means iodine has attained 14 electrons in its valence shell after the formation of 7 bonds with 7 fluorine atoms. Why iodine is capable of attaining 14 electrons, that is expanding its octet, that is to attain electrons more than the number of 8 electrons. Why so? Because iodine is available with vacant d orbital in its valence shell. So let's discuss about this thing in the hybridization. Now here first of all, central atom. In this case the central atom is iodine. Why so? Because iodine is forming maximum number of bonds, that is 7 bonds in the Lewis structure. So iodine will be the central atom. Now iodine is a member of group number 17. That's fluorine, chlorine, bromine, iodine and the astatine. After that, let's mark the period numbers. The fluorine belongs to period number 2, then 3, then 4, iodine belongs to period number 5 and astatine belongs to period number 6. After it, what's the general electronic configuration of group number 17 elements? That's ns2np5, where n is my period number, where n is our period number. That means the electronic configuration, the valence electronic configuration of iodine comes out to be 5s2 5p5. Now we got the electronic configuration, the valence electronic configuration of iodine. Now let's talk about the hybridization now. So iodine, we got its electronic configuration to be 5s2 5p5. Along with 5s and 5p, the iodine is also having 5d in the fifth shell with 0 electrons, that is vacant d subshell, or we can say the vacant d orbitals. Now let's make the electronic configuration of iodine in the form of boxes. So I'm going to represent the orbitals in the form of boxes, and we are going to fill the electrons according to electronic configuration. So we know that the 5s subshell has 1 orbital. So I have signified that 1 orbital with the 1 box. Now let's talk about the 5p. The p subshell always have 3 degenerate orbitals. Degenerate orbitals stands for orbitals with equal energies. So I have shown 3 boxes, and that's the 5p. Now let's talk about the 5d. In case of 5d, we have 5 degenerate orbitals, that is orbitals with equal energies. That's why I have shown 5 boxes collectively for the 5d subshell. So now let's fill the electrons. The 5s is having 2 electrons, so I'm going to fill 2 electrons in the 1 box of 5s, or we can say 1 orbital of the 5s. So that's the first electron with the spin of plus 1 by 2, and that's the second electron with the spin of minus 1 by 2. Now let's come to the 5p. In 5p we have to fill the 5 electrons, and I'm going to fill that 5 electrons in the degenerate orbitals of 5p according to the Hund's rule. Hund's rule states that in case of degenerate orbitals, firstly all the orbitals will get 1 electron each with a spin of plus 1 by 2. After that the pairing will start. So I have to fill the 5 electrons. So that's my first electron with the spin of plus 1 by 2, second electron with the spin of plus 1 by 2, and the third electron with the spin of plus 1 by 2. So that means here firstly all the degenerate orbitals has got 1 electron each with the spin of plus 1 by 2. Now I'm going to start the pairing from the fourth electron. So that's the fourth electron with a spin of minus 1 by 2, and that's the fifth electron with the spin of minus 1 by 2. So first of all, we got the electronic configuration in the orbital diagram for the iodine. So first of all, this is called the ground state electronic configuration. You can simply mention the ground state over here. After that, let's come to the Lewis structure. In Lewis structure, iodine is forming maximum of 7 covalent bonds, and we can say that all the bonds are single bonds between the fluorine and the iodine. That means all the bonds are sigma bonds, so we got the 7 sigma bonds. That means for the formation of 7 sigma bonds, iodine atom must have 7 orbitals containing 1 electron each that can overlap with the atomic orbitals of 7 fluorine atoms containing 1 electron for the formation of 7 sigma bonds. So let's come to the orbital diagram over here. So first of all, iodine must have 7 orbitals containing 1 electron each for the formation of 7 sigma bonds, and for that case we have to excite some electrons from 5s and 5p to the 5d to arrange that, to get that 7 atomic orbitals containing 1 electrons. So what's gonna happen? The 1 electron from 5p will get excited from 5p to the 5d. Now the second electron from 5p which got paired up will also excite from 5p orbitals to the 5d orbitals. After that, the 1 electron from 5s will excite from 5s to the from 5s to the 5d orbital. So we have to excite firstly only that electrons which are paired, and by exciting the 3 electrons, the one from 5s and 2 from 5p to the 5d orbitals, we will be having 7 atomic orbitals which are having 1 electron. So I'm going to make the excited state now. First of all, that's the 5s. That's 5p, 3 degenerate orbitals of 5p, and these are the 5 degenerate orbitals of 5d. In 5p we got the 3 degenerate orbitals, in 5d we have the 5 degenerate orbitals. So now let's fill the electrons. Initially 5s was having 2 electrons, now it's having 1 electrons. In case of 5p, initially 5p was having 5 electrons, now it's left with 3 electrons. Initially 5d was having 0 electrons, now the 3 electrons will be present in 5d, so that's the first electron, second electron and the third electron, and that's called our excited state. After that, as all these atomic orbitals, these 7 atomic orbitals will be forming 7 sigma bonds with 7 fluorine atoms, so from this step there will be the intermixing of atomic orbitals, and all the atomic orbitals containing electrons will be involved in the hybridization process. So during the hybridization, first of all, only those atomic orbitals intermix which have the lone pair of electrons and the orbitals which are going to form the sigma bonds. In this case, all the bonds are sigma. So here, all the atomic orbitals will intermix to form the hybrid orbitals. So in this case, I am writing 1 s orbital, 3 p orbitals and 3 d orbitals will intermix. Now this intermixing of atomic orbitals is called hybridization. In this intermixing procedure, we are involved with 7 atomic orbitals, the 1 from s, 3 from p and 3 from d. So total 7 atomic orbitals are mixing. So we will have 7 new hybrid orbitals. We are going to have 7 new hybrid orbitals. So I'm making the 7 new hybrid orbitals come degenerate orbitals. That is, the 7 orbitals will be of equal energies. So I'm making 7 new hybrid orbitals, and I'm showing that atomic orbitals collectively because they are all degenerate orbitals. So what type of hybrid orbitals we will get? As there's the mixing of 1s, 3p and 3d atomic orbitals, so the name of hybrid orbital will be sp3d3. Second hybrid orbital is also sp3d3. The third one is also sp3d3. Fourth one is also sp3d3. Fifth one is also sp3d3. Sixth one is also sp3d3. And seventh one is also sp3d3. Now, we are having 14.28% S character, 42.84% P character, and 42.84% D character. Per hybrid orbital. So that's the composition of our hybrid orbitals. That is, we are having 14.28% S character, 42.84% P character and 42.84% D character per hybrid orbital. Now, the atomic orbitals which are mixing, that is 1s, 3p and 3d, are having in total of 7 electrons. I can count them for you. So that's the first electron, second, third, fourth, fifth, sixth and the seventh. So in total 7 electrons were present. So now we have to redistribute that 7 electrons in the hybrid orbitals according to the Hund's rule. So that's the first electron, second, third, fourth, fifth, sixth and the seventh. So now let's talk about the fluorine atom. Fluorine, its atomic number is 9. The valence electronic configuration in terms of subshells and orbitals will be 2s2, 2p, 5. In 2p, we all know that we are having 3 degenerate orbitals. And these degenerate orbitals are having in total of 5 electrons. So that's the first electron, second, third, fourth and the fifth. So let's come over here. Here we have to make these 7 fluorine atoms, and I'm making their p orbitals. So first of all, that's the 2p of first fluorine atom, which is having 5 electrons. So that's the first, second, third, fourth and the fifth. In 2p, we are left with one atomic orbital which is having 1 electron, and this atomic orbital containing 1 electron is going to have head-on overlap with the sp3d hybrid orbital of iodine for the formation of sigma bond. So this sigma bond will be sigma sp3d3p, because this sigma bond has been formed by head-on overlap of sp3d3 hybrid orbital of iodine with the p orbital of fluorine. Now let's talk about the second fluorine atom. That's the 2p of second fluorine atom, which is having 5 electrons. So let's fill that 1, 2, 3, 4 and the 5. In this case also, we are having one atomic orbital which is having 1 electron, and this atomic orbital containing 1 electron is going to have head-on overlap with the sp3d3 hybrid orbital of iodine for the formation of sigma bond. So this sigma bond will again sigma sp3d3p. Now let's talk about the third fluorine atom. That's the 2p of third fluorine atom, which is having 5 electrons. So that's the first electron, second, third, fourth, fifth. Here also we are having one atomic orbital which is having one electron, and this atomic orbital containing one electron will have the head-on overlap with the sp3d3 hybrid orbital of iodine for the formation of sigma bond, and this sigma bond is again sigma sp3d3p. Now let's talk about the fourth fluorine. That's the 2p of fourth fluorine atom, which is having 5 electrons. So that's the first electron, second, third, fourth, fifth. Here also we are left with one atomic orbital which is having one electron, and this atomic orbital containing one electron will have the head-on overlap with the sp3d3 hybrid orbital of iodine for the formation of sigma bond, sigma sp3d3p. Now let's talk about the fifth fluorine atom. That's the 2p of fifth fluorine atom containing 5 electrons. So that's the first electron, second, third, fourth, fifth. Here also we are left with one atomic orbital containing one electron, which is going to have head-on overlap with the sp3d3 hybrid orbital of iodine forming the sigma bond, and that's sigma sp3d3p. Now let's talk about the sixth fluorine atom. That's the 2p of sixth fluorine containing 5 electrons. So that's the first, second, third, fourth, fifth. And here also we are left with one atomic orbital containing one electron, which is going to have head-on overlap with the sp3d3 hybrid orbital of iodine forming the sigma bonds. That's the sigma sp3d3p. At last, let's talk about the seventh fluorine atom, the last one. That's the 2p of seventh fluorine containing 5 electrons, 1, 2, 3, 4, 5. Here we are having again one atomic orbital containing one electron. So that atomic orbital of 2p containing one electron will have the head-on overlap with the sp3d3 hybrid orbital of iodine forming the sigma sp3d3p sigma bond, because this sigma bond has been found by head-on overlap of sp3d3 hybrid orbital of iodine with the p orbital of fluorine. That's why all the sigma bonds have been named as sigma sp3d3p. Now, so that's all about the hybridization of iodine atom in IF7. Now, let's talk about the structure or geometry, we can say. IF7. Here central atom is iodine, whose hybridization came out to be sp3d3. For sp3d3, we are having standard structure of pentagonal bipyramidal. So let's make it. First of all, iodine is over here. That's the first fluorine atom, the second fluorine atom, the third fluorine atom, fourth fluorine atom, and the fifth fluorine atom. So that's the first sigma bond, the second sigma bond, the third sigma bond, the fourth sigma bond, and the fifth sigma bond. Now, I'm just imaginary linking the fluorine atoms. They are not joined. Just to make you understand this structure in 3 dimensions, I'm making these dotted lines. Please don't get confused. These dotted lines are not bonds. I'm saying it again. So this is the pentagonal plate where all the angles are of 72 degrees. Now we are left with 2 fluorine atom, and that 2 fluorine atom will occupy the axial position. That's the fluorine over here, and second fluorine over here. So the two fluorine atoms are present on the axial positions. So these are called the axial bonds, and the other 5 fluorine atoms are on the equatorial plate. So these bonds are called equatorial bonds. And the bond angle of axial bond with the equatorial plate is of 90 degrees. Just try to imagine this in 3 dimensions. So that's all about the structure of IF7, and that's all about the hybridization. At last, let's talk about the energy points. In each and every hybridization, there are two types of endothermic processes, and they are, first of all, the excitation or the promotion of electrons from 5s and 5p to the 5d. So there's the energy required for the promotion of electrons. So at this point I'm writing, at this point here is the consumption of energy called promotional energy. That is the energy required for the promotion of electrons from 5s, 5p to the 5d. Now another type of energy required here is the intermixing of atomic orbitals. So here the endothermic process will be termed as hybridization energy. So at this point here is the consumption of hybridization energy. It is the energy required for the hybridization process, or we can say energy required for the intermixing of atomic orbitals. So we got the two endothermic processes. Now here we will have now one exothermic process, which is the energy released during the formation of 7 new sigma bonds. I am writing, the energy is released during the formation of 7 new sigma bonds between sp3d3 hybrid orbitals of iodine and p orbitals of fluorine. So the energy which is liberated compensates the, I'm writing, which compensates the promotional energy as well as hybridization energy, as both the endothermic processes has been compensated during the energy released by the energy released during the formation of 7 new sigma bonds between the hybrid orbitals of iodine and the p orbitals of fluorine. So I'm repeating it again. The two endothermic processes, that is promotional energy and hybridization energy, are compensated by the energy released during the formation of 7 new sigma bonds between the hybrid orbitals of iodine and the p orbitals of fluorine. That's why the formation of IF7 is chemically feasible process, or we can say spontaneous process, or we can say practically it's a possible process or chemically feasible process. So that's all for hybridization sp3d3 by taking an example of IF7. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of friends. Don't forget to press the subscribe button. Stay blessed.